Hi everyone, in this video we will be discussing the IGCSE chemistry topic of stoichiometry. In this video, we will be focusing on the relationship between the number of moles of a substance, its mass in grams, and its relative atomic or molecular mass. To ensure that you're able to get the most out of this video, it is a good idea to ensure that you have a periodic table in front of you, as well as a scientific calculator. So let us first look at this chemical equation. Here we have the combustion of hydrogen in the presence of oxygen to form water. Let's say we're given the information that 8 grams of hydrogen was used. How can we work out how many grams of oxygen is needed and how many grams of water is produced? We can see in the equation that the number of molecules of oxygen is half of the number of hydrogen molecules used, 1 to 2. So since we know this, would it be correct then to say that the mass of oxygen is half of the mass of hydrogen used? And since we know the mass of hydrogen used, we can say that the mass of oxygen should be 4 grams, which is half of 8 grams. And by extension, since the number of molecules of water is the same as the number of molecules of hydrogen, would it be correct then to say that the mass of water produced is equivalent to the mass of oxygen used, which is 8 grams? Now pause this video for a minute and think. Both of the previous assumptions are wrong because the coefficients are these big numbers on the equation, are molar ratios, not mass ratios. 2H2 means that there are 2 molecules of hydrogen. 1O2 means that there is 1 molecule of oxygen. And that's not the same as saying that 2 grams of hydrogen reacts with 1 gram of oxygen, because hydrogen and oxygen has different masses. Now there are a few ways to solve this problem. One way is to work out the mass ratios. Recall that in the previous solution, it doesn't work because these numbers are molar ratios. They are ratios of the number of molecules and not the ratios of masses. So if you want to relate the mass of one reactant to the mass of other reactants and other products in the equation, then we will have to find the mass ratios. So how do we find the mass ratios? We will need to know how heavy oxygen, water, and hydrogen are relative to each other. So if you have your periodic table with you, you should be able to see that one of the values available for all elements is the relative atomic mass. Now, in this video, we're not going to go into what the relative atomic mass is. For most intents and purposes, we can think of the relative atomic mass as how heavy each element is relative to each other. So we can see that hydrogen has a relative atomic mass of 1. So an element with a relative atomic mass of 4, for example, helium, would be 4 times as heavy as 1 atom of hydrogen. To find the ratio of masses, we're going to use this balance equation here, and we're going to work out what are the relative masses of every single species in this equation. So let's just go ahead and add up all of the relative atomic masses of every single element in this equation. So for 2H2, that's 2 times 1 plus 1, that's 4. For oxygen, that's just O2, so that's 16 plus 16, so that's 32. For 2H2, that's 2 times 1 plus 1 plus 16, that's 36. Now that we have the relative masses, we can calculate the ratio of these masses, and we want this ratio to be compared to the species with the known mass. In this specific example, the species with the known mass is H2, which is 8 grams. Taking oxygen as an example, we will compare its relative mass of 32 to the relative mass of hydrogen in this equation, which is 4. 4 to 32 is equivalent to 1 to 8. In other words, we can see that in this reaction, assuming that the reaction is complete, the mass of oxygen that was used is 8 times that of hydrogen. And now that we know how much mass of oxygen was used in this reaction relative to hydrogen, we can finally work out how much mass of oxygen is used in grams. We know that the mass of oxygen used is 8 times greater than the mass of hydrogen used. The mass of hydrogen used is given in the question, that's 8 grams. So 8 grams times 8 is 64 grams. We can use the same logic to work out how much water is produced. We compare their relative masses. Remember that you should always compare the relative masses to the species with the known mass. And in this specific example, that's hydrogen, which is 8 grams. Right, so the relative masses is 4 to 36, which simplifies to 1 to 9. Now that we have the mass ratio, we'll do the same thing as with oxygen earlier, and we'll work out how much water was produced in grams. We know that the mass of water produced is 9 times greater than the mass of hydrogen used, so 9 times 8 grams gives you 72. So this is one way we can work out how many grams of reactant is needed and how many grams of products are produced, as long as we have the balanced chemical equation and the mass of at least one species in the reaction. Stoichiometry is a very calculation-intensive topic, so it's unlikely that you'll be able to remember much of what was discussed if you do not practice it. Let's go ahead and pause this video and try to solve this question. Let's go over this question and let's see step by step how to work out how much oxygen is needed and how much carbon dioxide is formed. Now, the first thing we need to do is to get a balanced chemical equation. So in this equation, we have one carbon atoms reacting with one oxygen molecule produces one molecule of CO2. So the coefficients here are all 1, 1, and 1. Next, we're going to find the ratio of the relative masses of every species in this equation. And to do this, we're going to need the relative atomic masses of every element in this equation, and that's carbon and oxygen. So the relative atomic mass of carbon is 12, the relative molecular mass of the oxygen molecule is 32, and for carbon dioxide, it's 44. Next, we're going to find their mass ratio relative to the species with the known mass. And in this question, the species with the known mass is carbon. So we want all the mass ratios to be relative to carbon. So we can see that the mass of oxygen used is 32 over 12 times that of carbon. The mass of carbon dioxide produced is 44 divided by 12 times that of carbon. Now finally, let's work out the mass in grams of oxygen and carbon dioxide. We can see in the previous step that the mass of oxygen used is 32 over 12 times that of carbon. And we know that the mass of carbon used is 24 grams, so that's 24 times 32 divided by 12. That gives you 64 grams. And we do the same with carbon dioxide, and that should give you 88 grams. If you're able to follow this far, well done. If not, pause this video and let's rewatch from the beginning again. If you managed to solve the previous question, here are a few more to challenge you. So pause this video and work out the answers to these two questions. Once you're done, go ahead and post your answers in the comment section below. We have looked at one approach to work out the mass of different species in an equation, as long as we have the balanced chemical equation and as long as we know the mass in grams of at least one species. Recall that at the beginning of the video, we discussed how we cannot use these numbers, these coefficients directly, because these coefficients represent the number of molecules, they are the molar ratios, and not the mass ratios. And we solve this by working out the mass ratios of the different species in the reaction. But that seems like a waste because we already have these coefficients over here. It just seems like a lot of wasted effort to work out the mass ratios when we already have the molar ratio. So now we're gonna look at another way of solving this kind of problem by using the molar ratio directly. How can we do this? So recall the example in the beginning of this video. We mentioned that we can't use these coefficients directly because these coefficients are number of molecules and not mass. And the problem is different elements have different masses. We can solve this problem if we can just work out how many molecules are in 8 grams of hydrogen. Then we can use this ratio directly because that's exactly what this is a ratio of number of molecules. So we need a process, we'll call it process A, that converts the mass in grams to the number of molecules. And we'll call the result of process A to be X. And now we know that 8 grams of hydrogen contains X molecules of hydrogen. We don't know what the value X is yet, but we'll just call it X for now. And we can see that the number of molecules of oxygen is half of hydrogen, so that is 0.5x. And we can see that the number of molecules of water is the same as hydrogen, so that is x as well. So to work out the mass in grams of oxygen and water, we just need the reverse of process A. Now we're going to learn what process A is, and we're going to begin by introducing the mole concept. So you probably know that one pair of anything consists of 2 units of something. 1 dozen of something contains 12 units of whatever that something is. Much in the same way, 1 mole of something is 6.023 times 10 to the 23 units of something. And this is also the current IUPAC definition of a mole. 6.023 times 10 to the 23 is called Avogadro's number or Avogadro's constant in honor of the chemist that made a lot of contributions in this field. Historically, a mole used to be defined as the amount of substance that contains the same number of particles as the number of carbon-12 atoms in 12 grams of carbon-12. But presently, it is more simply defined as just 6.023 times 10 to the 23 units of something. And the number of moles of a substance is related to the mass in grams of that substance through this mathematical relationship. The mass in grams of a substance is equal to the number of moles of that substance times its relative molecular mass. Relative molecular mass is just the sum of all relative atomic masses in that molecule. So now let's use this relationship and try to work out a simple problem. Let's say if we want to find the number of moles in 24 grams of carbon. So we know that this is what the relationship is. So to find the number of moles, we should make the number of moles the subject, which means the number of moles will be equivalent to the mass in grams divided by the relative atomic or the relative molecular mass. And in this case, that's 24 grams divided by the relative atomic mass of carbon, which is 12. So 24 divided by 12 is 2 moles, right? So there are 2 moles of carbon atoms in 24 grams of carbon. In terms of the number of atoms, that's 2 times 6.023 times 10 to the power of 23 atoms of carbon. Now, this is one of the most common equations that you will encounter in stoichiometry, so it's very important that you're comfortable with using it. Let's pause this video and solve these questions. Now, let's use this new mathematical relationship and solve the problem that we face at the beginning of this video. So early on, we said that it will be good if we have process A, which converts the mass in grams of hydrogen to the number of molecules of hydrogen. And we have just learned what process A is. Process A is this mathematical relationship. We're given the mass in grams of hydrogen. We can work out the relative molecular mass of a hydrogen molecule using a periodic table. The relative molecular mass of hydrogen is 2, so we should be able to work out the number of moles of hydrogen that was used. So let's go ahead and do that. Number of moles of hydrogen that was used would be equivalent to the mass in grams divided by the molecular mass of a hydrogen molecule. So that's 8 grams divided by 2. So that's 4 moles. So let's go ahead and replace X with 4. Now that we know that 4 moles of hydrogen was used, we know that the number of moles of oxygen used is half that of hydrogen. We know that half of 4 is 2. So the number of moles of oxygen used is 2 moles. By using the same logic, we can see that the number of moles of water produced is the same as the number of moles of hydrogen used. X for water should be 4 moles. So now, to work out what is Y and what is Z, we just need to reverse process A. So to find the mass of oxygen used, we just need to multiply the number of moles with its relative molecular mass. So that's 2 times 32, giving you 64 grams. And we do the same with water. That's 4 moles of water times the molecular mass of water, that's 18, so giving you 72 grams.